Hi everyone. Good morning, good evening, good afternoon, like from whichever part of the world you guys are joining from. I'm Shadab. I co-founded Quantum Computing India back in 2019, and today we have Johan from Gluon. He is going to deliver the talk on quantum computing for Java developers. And thanks, Johan, for accepting the invitation and coming to share with us something new, which most of the developers I think would be looking forward to learn about. Because me as a Python developer, uh, we have so many SDKs, libraries, packages, and support to code in Python, but we don't have enough resources if we have to move to some other languages. Like Java, this is like it is one of the most used programming language for developing applications and softwares. And there are many Java developers across the world, but they are not very much sure like how they can start it with quantum, or if Java can be used uh, for using some for building some of the application, right? So yeah, so in coordination with Washington Quantum DC, which was started by Professor Dev, and Helen is managing this meetup group. If you have not heard about this and directly joining from some other link, I will suggest go and check Washington Quantum DC meetup group on Meetup or LinkedIn, or you can ping me, Helen, or Professor Dave, anyone, and we will share the link with you. And we have other supporters like who are leading quantum communities or quantum organizations across different geographical locations, like Quantum AI, Association Quantum, Cambridge Quantum, and many other. We had we have done many events in past, like each month at least one or two events will be happening, and there'll be a lot of learning opportunities for you, for everyone. And we have certain meetup groups lined up for the next month as well. So I think this is the last meetup of 2022, and I'm really glad that during the holiday season also so many people have turned to learn something today. So on Jan 14th, like starting in 2023, 3 a.m., we have Dr. Catherine, who is a quantum evangelist at Quantinium, and she will be talking about TKIT, which is an advanced quantum SDK. So uh, that you can plan to attend next. And we have many other events like in Jan 29, Anna, she will be talking about error mitigation and error correction. And on Feb 4th, we have another upcoming meetup for which John will be presenting. Topic will be combining ethics and excellence in the quantum workforce. And this is also like very important topic, right? How to think of ethics and excel in the building the quantum workforce who will be leading the quantum development and research in future, right? So John and Natalia, she will be talking about, they will be talking about basically, and Dr. Rupesh. So these three will be the panelists having a discussion and putting some good thoughts around that. Next, we have quantum computing tool chain, for which Ron would be the speaker on Feb 11th. And on March 4th, Brian will be talking about dynamic quantum circuits. And I'm glad Ron is also available on the chat. Thanks, Ron, for joining. And these are the other sponsors: QWorld, QBNet, Quantum AI Foundation, Q Poland, and all. So I'm really hoping like you will not stop your learning if you're joining us for the first time. Then there are so many amazing talks lined up for the new year as well. You can see in Jan and Feb, uh, Helen and Professor Dev, they have fully packed the agenda. I hope everyone join those sessions as well. And today we have Johan from Gluon. He's like a Java developer working in the industry from 1995, and he has been part of the industry like coding in Java from back 1995. He was part of Blackdown team that time. After that, he co-founded his own company Gluon, which was responsible for enabling mobile and embedded Java level enterprise level Java softwares basically. And Johan is a Java champion and member of the Revox steering group as well. And he is one of the authors of the Pro Java FX book and the author of Quantum Computing for Developers as well. And He is well-known speaker who has spoken across numerous conferences, and he and Gloon received a Duke's Choice Award in 2014 and 2015. And he also contributes to a number of projects, including OpenJFX, OpenJDK, GraalVM, and he's project lead for OpenJDK Mobile and co-lead for OpenJFX. So there's a lot of hat which Johan is wearing, and I'm definitely sure, like, it's honor for us to learn from you, Johan, about like how Java can be utilized in developing applications using quantum principles. So over to you. I will stop over here.
Thank you very much for the introduction, and I'm really honored to be speaking here.
Same here,
I'll
Johan.
share my screen. Right, I think people can see my screen now. If there are any questions, I will keep an eye on the chat every now and then. So while I'm trying to explain things, if things are not clear or if there are some issues or questions, please ask them. I'll probably try to answer some of them right away, and maybe other questions might be answered at the end, or when I know that that's something that I will tackle later, I will do that. But I really want to get as much feedback as possible. It's actually a difficult presentation. I mean, presentations on quantum computing are never really easy, but especially this presentation is about the middle between quantum computing and classical Java development. And one of the reasons why I wrote this book and wrote a simulator is because I feel there's a big gap between Java development or legacy IT development in general, and on one hand, and on quantum computing on the other hand. So trying to accommodate people coming from both different ends is a challenge, but let's see. So I'll first give an outline of how I try to structure this talk, and I'll start with classical computing. So this is something that current Java and enterprise developers are familiar with. So how does high-level classical computing look like? And then we see how that goes to low-level computing. So high-level classical computing is typically well, just some code. Then we have low-level classical computing. How does that translate the code that you as a developer write? How does it translate to the hardware? And then we have a breaking change. What is the difference between classical hardware and quantum hardware? And then how can we go up from low-level quantum computing to high-level quantum computing and back to a Java application again? So that is the outline that I suggest. And how much time I spend on the different topics depends on how fast I go and how and if I go too fast or too slow, then let me know and I'll try to adjust. So yeah, I think about me there's not much more to say apart from maybe that I did my PhD in at Delft University at the Faculty of Applied Physics. And in order to, it was about the acoustic wave equation. So wave theory has always been very interesting to me. And in order to do computations and visualizations, I realized that IT is very important. And there, a language like Java was extremely, it was very new at that moment, and it was very appealing to me. And I think it is even more today because most of the backend software that's currently in the world, and I think all of the Fortune 500 companies are using Java in their backend applications. So I think it's a real challenge to, first of all, it's already a challenge to keep Java and JavaFX maintained. up to date with modern development paradigms. And second, it's even more challenging to keep it up to date with radical evolutions in, for example, quantum physics. So, and that is why I'm fully aware that most of the resources on quantum computing are in Python or similar, and I think Python is a great language, so that's totally fine. But what we often see is that works very well for proof of concepts, and lab experiments and showcases are extremely important. But if then you want to bring this into production and you want to integrate it with existing software, then there's a big gap between the Python and the Java world. So with this book that I wrote, and I'm pretty sure that the discount code, I wrote it there. I'm not really sure that I'm actually pretty sure that it's, so this is the book, that it's still valid. You get a major discount on the products. Now, keep an eye, if you want to buy this from the Manning website, keep an eye on that. During the holidays, they have a number of days where all products are 50% discount. So that's, of course, even better than the 35% discount here. But so with this book, I especially wanted to target Java developers who know that quantum computing is something that might be coming, but who also want to know, how is it relevant to me? Do I need to care as a Java developer, or is this just something science fiction for in 5 decades from now or so? So that is the approach that I am taking in that book. So that is a bit about the bridge between Java and quantum computing. So let's get started with classical computing. So this is some Java source code. It's from JavaFX. JavaFX being the UI framework, the de facto standard to create user interface applications in Java. And the details of this code are not relevant, but the important part is that as a Java developer, but I think as a developer in general, you can read this code and you more or less understand what is happening. I mean, even if you don't know what is happening, it's at least you can nod and say, yeah, I see you're probably creating some content label and you want to set the width to some computed size or so. So that is more or less human readable. Even if you don't know the details what it is doing, it is human readable. And that is important because developers are humans. So not going into detail about AI doing development as well. So the Java developers, at least those of today, are humans who want to understand what they are writing. The problem is that the computer doesn't understand this. So we need to go lower in the stack. And the first step in this is the Java the Java compiler is going to translate this Java source code that you saw on the previous slide into Java bytecode. And that is demonstrated here. So there are a number of bytecodes defined in the Java programming language that translate your human readable source code into Java bytecode. And that is still a bit readable to low level Java experts. This is pretty much readable. But to a machine, this is not readable yet. The advantage of Java is that this is readable to all different Java installations on different platforms. But if we really want to execute it on a machine, we need to go one step lower, and we have to translate the application into machine code that the CPU and the core processing units on the machine can understand. So I just made this up, this machine code. So this is not the code that's being translated from the previous slide. So if you want to reverse engineer that, this will probably lead to nothing. I actually don't remember how I generated it, but anyway, so this is something that that's already close to what machines can understand. But actually, we're not there yet because it still needs to be translated into bits. At the previous slide, you saw byte because that's what's typically used by traditional CPU architecture. If we group bits into bytes and then we can group them so the hardware structure and address space of computers take advantage of packing bits into bytes and other structures. But the zeros and the ones, that is actually the heart of a classical computer. And everything that is stored and everything that is operated on can be expressed as a combination of 0 and 1s or as a manipulation of the zeros and the ones that do this. And how are these zeros and ones then altered or manipulated? That is by applying gates to the bits. And for example, this is a very simple gate, the NOT gate, that is inverting the value of a bit. So if the bit is initially 0 and a NOT gate is applied, then the resulting value, did I say? Okay, let's do this again. If a bit is initially 1 and a NOT gate is applied, then the resulting value is 0. And vice versa, if the bit initially was 0 and the NOT gate is applied, then the resulting value will be 1. So that is a simple operation on a bit that's done by a classical computer. And as a Java developer or any other high-level programming language, you don't have to do this yourself, but the code that's being translated by the compiler and by other stuff is going to do this for you. So if the input is, as I said, if the input is 1, the output will be 0. If the input is 0, the output after applying this gate is going to be 1. And if the input is some combination of 0 and 1, what is the output then going to be? Now, this is a question that's totally nonsense in the classical context. And in a typical classic Java development, you really don't need to consider this, and it's very weird, of course. But the zeros and ones that we're using in classic computing are actually artificial constructs, because nature itself isn't digital, and the fundamental properties. So this is probably something I think, I don't know how much percentage of the audience is has a quantum background and how much has an IT background. So, and I always feel that what I'm saying here is way too simple for the IT people, and now this is way too simple for the quantum people. But anyway, there we go. The fundamental properties in nature, at least some fundamental properties, cannot simply expressed as a 0 or 1. It's much more complex, and I don't want to go into the details of the wave equation that defines the probabilities and the possible evolutions. But for development, for IT development, it's most often enough to understand that some properties, fundamental properties, can be a linear combination of 0 and 1, which means, and I will repeat this a few times from different angles, which means that we can only tell that if we would measure this property, that there is a probability of X% that we will measure 0, and some other probability that we will measure 1. That's the only thing that we can tell. And this is called a superposition of two values. So the property is, it can be 1, it can be 0, but it can also be some combination of 0 and 1. And this is, of course, the for quantum physicists, the obvious thing, but for ITers, it's often the weird thing. And the typical experiment that explains this to people is the double slit experiment, where an electron beam gun is used to send individual particles through one of two through the double slit material, so which is a material with two slits, and then one would expect without quantum effects that if you do this one by one, that the particle will either go to the left or the right, and you would see two areas where particle lands. But it can be proven that this is not the case, and that the particle behaves as a wave, even if it's just one single particle. So this is actually not relevant to IT development, to IT developers. But the reason it is important is that quantum computing is not something that is invented as a theoretical exercise. There's really practical evidence that the foundations of quantum computing are really working. So it's not something that just has been invented, but it's really proven by experiments. So it's I want to debunk the myth that this is just something from theoretical physicists who do this, who invent things that are just needed to fix mathematical problems in equations. No, this is really something that's a physical phenomenon. And there are a number of properties in nature that can have this behavior, by which I mean they can be 0 or 1. They can, without knowing exactly is it 0 or 1. So this this non-binary state exists in some fundamental properties. And to make it easy, we call all these properties qubits. So a qubit, which is of course the quantum equivalent of a bit. A qubit is in general something that can hold a value 0, a value 1, or a combination of the 0 and the 1. And that is similar to how a bit is something that is 0 or 1. So it's actually an extension of a bit. But it's a major difference, at least at the low level part, is then that quantum computing, relying on quantum physics, is more about probabilities and less about measuring values. So if what we actually the values of a qubit do not represent the value that you would measure, but it's rather how big is the chance that if we measure this now that we would measure a 0, and how big is the chance that we would measure a 1. So in the quantum part, we rather talk about probabilities instead of deterministic values. So to look at it from another way, we can describe the state of a qubit as it's typically done in Greek letters. For example, the psi that you see here, and the notation, the bracket notation. I'm not going to in detail about that. Expresses the qubit value, so that it can be a 0, which corresponds to what in classical computing we call a Boolean false. It can be 1, which in Java is the Boolean true, but it can also be a combination of 0 and 1, and we don't have an equivalent of that in Java or in any other classical language. And what you see here is at the bottom is that this actually means that for one qubit we have a value alpha and a value beta, and we have, so because it can be 0 and or it can be a combination of 0 and 1. One qubit actually holds 2 values, and that is very relevant for scaling, because and this is a very dangerous slide. So I'm always careful to say how to say this, because I don't want to have people going crazy with whoa, that's magic, because there's no magic here. It's just simple laws of nature. So, but in classical computing, if we have 1 bit, that bit can hold 1 value. It's either 0 or it's 1. But in quantum computing, 1 bit can hold 2 values. And if we extend that, in classical computing, if we have 8 bits, those hold one specific value. It can be 0, 1, 1, 1, 0, 1, 0, for example. But in quantum computing, 8 qubits actually, so it should not be bits, but qubits. 8 qubits can hold 256 values with different probabilities. So there might be 1% chance that if we measure it, it measures 0.00001 and so on and so on. But it can hold all these values simultaneously. And I know some people would kill me if I use the word simultaneously. So, but it's a virtual event, so I'm pretty safe. And the main reason I show this is that it shows that the exponential nature of qubits can be used by problems that are exponential, that scale exponentially, because tackling those on a quantum computer is well, that's where a quantum computer is made for. On a classical computer, those are the problems that are hard to solve or close to impossible to solve. As an example, and this is the typical example, and I think it's a great one to get people's interest in quantum computing. It's also a dangerous one because this is something that's probably not the very first application of quantum computing. And I don't want to disappoint people, but most of the of today's encryption is based on the fact that it's easy to go from 2 prime numbers to the multiplication of that of those 2 prime numbers, but it's very hard to do the reverse operation. If I have a large number, finding out what are the factors that, if multiplied, create this large number, that's much harder. And it can be proven that if you want to solve this with a classical computer, that the more bits you add, so the larger the number gets, it becomes exponentially, almost exponentially harder to solve this problem. And that is why encryption techniques that are used today are so successful, because just adding 1 bit makes the problem to crack a code, to sort of reverse engineer a private key, makes it much harder. So just by adding a few bits, and the problem becomes almost impossible to solve with even all the computing power in the universe. If we would be able to solve this problem in a polynomial way, then it's a very different story, because then those keys can be cracked. And there is an algorithm, Shor's algorithm, that solves part of the factoring problem in polynomial time. So it's easier to crack the encryption by using Shor's algorithm. As I said, it's not really something that should be expected to be ready in as a first quantum application, but it's something that that typically draws attention from people to the problem. So, as you know, because I got a comment that so most people here are quantum. Probably quantum experts, so I'll talk more about the Java parts. So the question that I typically got from, or actually Java developers, is that if we're in a superposition, if we have so many different possibilities that can be held in one or in a set of qubits, then that's fantastic. So we can fix all problems. But the main issue then is that, as you know, when we measure a qubit, we don't measure the alpha and the beta. We just measure a single value. So once something is measured, we are back to classical values. And then people often ask, so what's the benefit in doing all of this? We can have 256 values simultaneously, but if we can only measure one value, then what's the value? The thing is that if you do the processing when you have different, when you can still have the different values in such a way that ultimately the value that you will measure gives you information about the problem, then that is the key to finding good algorithms. And I often compare it to the Java has this notion of streams where you can where operations can be done in parallel, and in the end, when there are when all the execution is done, there's a single result. So this is totally not using quantum computing, and it's totally not benefiting from qubits or so, because all this parallel processing is done on isolated resources. But it's the same concept. I mean, there are some similarities in the concept. It's that you want to, for example, find the biggest number or you want to find in a big list of records, you want to find that record with where the ID is matching a specific ID. With Java streams, you would be able to do you want to filter from all the records the one that matches the ID that you're given, and then you will get one result. And the filtering is done in parallel. And even if you only get one result, it can be extremely fast because you are using parallelization. So what you can achieve with quantum computing is this parallelization, but not by adding more hardware or threads, but just by leveraging the properties of nature. And that is something something that's pretty unique about quantum computing. I'll try to keep a balance between the quantum computing and the Java. But again, if more people want me to go faster in Java or slower in Java, then let me know. It's so my plan, the slide that I have now is that I first do the theoretical work that I'm doing now, and then I show the Java code. And that's going to work well because I can't seem to be unable to show slides and code at the same moment. But I'll go to Java code soon. So what are typical quantum computing applications? I think this is something if you talk about the quantum, I mean, if this is a quantum meetup, then you know them probably better than me. But I see applications for quantum computing in word security, interfactorization, for example, optimization problems. The search through unstructured data with core search, for example, is a typical one. And I personally have lots of hope for fixing problems that we have in chemistry and physics and understanding nature in general. I personally think, and I will show some code there, that one of the main applications that we will see first is more about quantum networking, because that requires not many qubits, and that can make quantum that can make communication much more secure. So that's something that works in two ways. Quantum computing is often in popular press said to be a danger for encryption because it can break encryption, and many companies are now working on post-quantum cryptography. But on the other hand, quantum computing really allows for secure encryption, and with just one qubit on every device, we can achieve this. So I personally hope that is an area that will be one of the first real world solutions using quantum physics. So we're now moving from the low level, we're now at the low level quantum physics, and we want to move up. So how do we have this qubits that we do understand can be 0, 1, or a combination of 0 and 1? What can we do with them? And there is some sophisticated hardware which I'm extremely amazed when I see this, and I have the biggest respect for the experimental engineers who are creating this. How can you yeah, it's typically done with lasers, but how can you manipulate the state of such a tiny fundamental particles? But it is possible. So whereas a bit can be changed between 0 and 1 by sending some current through a transistor, a qubit, the state of a qubit can be changed as well. And that is, of course, needed to well, to do something useful with qubits, or to do something useful with quantum in general. So the number one question, or no, a question that I very often get when talking about quantum computing is, are you doing this on a quantum computer? And then the answer is, well, of course, and or unfortunately, no, not at this moment. The quantum computers do exist. And I think they're, in my opinion, they are good enough to prove that the theory is working. So that that these are not just theoretical predictions, but that it's really something that works. But it will still take a long time before the computers are capable enough of doing something very useful that a classical computer can't do. And what I write here about sufficiently large number of qubits for a sufficient long time is actually more complex than that. And I personally think IBM did a good job a couple of weeks ago in expressing how they measure the quality of qubits and and everything around. So it's a complex area. Different companies are making progress, but we're not there yet. But that's actually not really needed to make progress on the software side, because we do know the basic laws, and we can use existing classic computers to simulate those laws. And it's actually just come down to linear algebra. So it's not that hard to do. It is hard, of course, because what we get for free by nature, which is actually multiple states for one single qubit, is something that we don't have in classical computing. And to mimic that behavior, we need lots of memory. And so the more qubits that we want to simulate, the more memory that we need. And actually, if you think about it, it's a funny problem, because a transistor in a classical computer it's very small, but it's still very big compared to the quantum particles, because if a transistor was smaller, then it would not be a transistor, because then effects like quantum tunneling would destroy the goal of a transistor, which is being a barrier sometimes, so that no current can flow. So we created something that bypasses quantum effects, and now we are using that thing, the transistor, to simulate quantum effects. So that is actually double complexity, and in the end, using the real qubits is of course going to remove the double complexity. So that's why, even if quantum simulators are very slow or require lots of resources, the real quantum computers will not require this. So yeah, that's basically what I explained. We know the mathematics to describe quantum behavior, so we can simulate it. And as a Java developer, you should, if you're working on typical IT applications, you should not be aware of concepts like superpositions, because the moment that any value is measured, it's classic again. and it's unlikely that the Java developer will need to intervene in the quantum process. And I will explain this later. So where are we in the outline? I want to quickly focus a bit more on the difference between the low-level classical and the low-level quantum computing. So this is targeting the Java developers who want to understand the difference, and then we go up talking about how the low-level quantum computing can be translated in Java computing. So in classical computing, we have the transistor, and in quantum computing, we have a qubit. It's often depicted in a different way, but I personally favor the approach where we show a 0 and a 1 on in a single icon, because this shows that this qubit holds some 1 information and it holds some 0 state, and that is the difference between a classical computing and a quantum computing base unit. So the left part we already covered that. On a classical gate, on a classical system, a NOT gate will invert the value. 1 becomes 0 and the 0 becomes 1. And on a quantum gate, it's the opposite. Sorry, on a quantum gate, it's the same. 0 becomes 1 and 1 becomes 0. But a qubit that is in the state alpha 0 plus beta 1 will be inverted. So to the if this is new for you, so I explained this in very much detail in my book, chapter 4, I believe. But alpha correlates to the probability that if we would measure this qubit now, that we would get a value of 0. And beta corresponds to the probability that if we would measure it now, that we would get a value of 1. So you can see that the higher alpha is, the more likely we will measure 1. But if we then apply that X gate or the NOT gate, then you will see that it's now becoming more likely that we measure 1. But it's more likely. It's not that it will flip from 0 to 1. So that is the difference between the 0 and the 1. Between the classical and the quantum gates. So how is this? How do we achieve this? Well, how can we achieve this in a simulator? And the reason why I explain this is because the Java quantum simulator that I wrote is using this theory, and in order to understand something, it's often easier to explain it, and because by trying to explain it, you can understand it, and by writing a quantum computer simulator, you understand quantum computing better. So that's why I came up with this. In quantum, so quantum gates are often depicted as matrix operations applied to the probability vector. So before a quantum gate is applied, there's a probability that we will measure a 0 or 1. And after the quantum gate is applied, the probabilities are changed. And how are they changed? I'm not going into detail. I covered that in the book, but that is by multiplying the probability vector with a matrix. And that already explains, if we go higher now, that already explains the difference in complexity, because matrix operations are expensive, and that's why quantum simulators are typically difficult and slow. So operations on gates, on classical gates, are actually easy to calculate, because if you start with zeros and ones, you just follow the circuits and you see that, okay, so I have a 0 here, there's a NOT, so that becomes a 1, and that's easy. But in quantum, it's much more difficult, because you have to do matrix multiplications. What you see here on the right is a quantum circuit, which I will look into detail, created with Strange, the Java quantum simulator that I wrote, and that allows you to do basic quantum operations on qubits. So that software is specifically written for Java developers to play with the low-level quantum behavior. Note that I only talked about superposition and as a specific quantum behavior, by which we mean that a qubit can be in a linear combination of 0 and 1. I did not talk about entanglement, and I actually don't plan to talk about it today unless yeah, you really want me. But what I learned is that for many Java developers that are new to quantum computing, it's too much information, and actually the concepts from a computing point of view are similar. So we will get more examples of how we can simulate quantum circuits in Java soon. So there's another difference between how quantum gates are behaving compared to classical gates, because quantum gates maintain the superpositions. So that means that we need, if we want to simulate that, we need to move the probability vector between every step. We need to calculate all the probabilities, and it is only at the very last moment when we want to measure the outcome of an algorithm that we will get a single value. But that is why we need to do many linear algebra calculations in a quantum computing simulator, because even if we have just a single outcome, ultimately every qubit that we measure will either be 0 or 1, and we don't know anything anymore about how likely it was. It's just one outcome that we have. But our simulator will calculate until the very last step what the probability is, and then it will choose one, just like a real quantum, or not just like a real quantum computer will do it, because the measurement problem is a whole different story. But let's not get there. So what is this quantum computing simulator that I talked about a number of times? It's called Strange, which is written in Java, and it's available on GitHub. And the code that a Java developer writes for Strange, which is currently only using a simulator, should work on real quantum computers as well, because it's the gates that Strange is using internally are proven to be realizable on real quantum computers. There are actually a limited number of gates required to create a whole set of gates. So that is one huge benefit, I think, and very relevant to existing developers, is that you do not need to wait before real quantum computers are available. The code that you write today will allow you to validate what you're doing. And I often compare this with the Millennium bug, the Y2K bug, where people in the 90s realized that many computer systems would stop working at the year 2000 because of the Y2K bug. So people were starting to write software long time before that hardware problem was going to occur, or that the Y2K problem was going to occur. And that is something that you can do as well now too. You can write software for quantum computers, and you can test this software on a quantum simulator like Strange. And then when quantum computers are really powerful, your software will run on a real quantum computer incredibly faster, much more performant than on a simulator. So that is one of the reasons why I highly recommend doing quantum computing on simulators already. In order to visualize it, I created a strange of X, which is written in Java and Java of X, and which visualizes the circuits created with strange. So the circuits that you saw, which I had on the previous slides, for example, consists of well, typically had this structure. So on the left-hand side, we show a qubit or a number of qubits initially in the 0 state, and then some gates are applied, or one gate is applied, and ultimately the result is measured. On means value 1, off means value 0, and typically there's going to be a percentage that says how likely is it that we're going to measure A or B. So here are the links to the GitHub repositories that have the code for the simulator strange, the code for the UI framework that visualizes it using strangeFX, and then I have a bunch of samples, and I will go through a few of these samples now, which are in the repository Quantum Java. So those are the samples that I discuss in my book. But I have a few other repositories as well, and I will add them to the slide. I will show samples, but because it's probably harder to switch between slides and code, I will first do the remaining 2 or 3 slides about the difference between low-level programming with strange and high-level programming. In low-level programming, what you do is you create a quantum circuit with gates, just using Java code, and you measure the results. So you're using gates, and so this is an example of low-level programming with gates. So it's using Java. So if you're familiar with Java, this will be very easy to you. Java critics will always say that it's pretty verbose, and that's fine. So it's Java with its specific properties, and I'm pretty pragmatic here. There are 12 million Java developers out there writing software for systems and enterprises and companies and academics and so on. And I really want those 12 million Java developers to be able to write applications that use quantum computing. And if they don't want to learn a new language for it, if they don't have to learn a new language for it, then that's even easier. So if they can use their existing skills to and leverage quantum algorithms to create, maybe ultimately find the cure against Alzheimer or so, then I'll be very happy. So that is my my motivation to do this in Java, to tap on this pool of so many talented engineers, to give them access to something that can really make lots of improvements to human. So what you see here is a simple Java class with a main method where we first create a quantum execution environment, a simulator, and then we create a quantum program, which is which contains a number of steps that will be applied to the qubits. A step contains one or more gates. In this simple example, we have only one gate, the X gate, the NOT gate, which is applied to the qubit with index 0. So that's added to the step. We add that step to the program, to the quantum program, and then we ask the simulator to run the program. Oh, by the way, if for example you're a Kotlin fan, all that it's written here can be written in a single step as well. So there are different patterns that have a more fluent or builder or functional style. So I try to accommodate the different flavors in the Java world. So we run the program and we get a result, and then what we can do is measure the result and print it out. And because we started with 0 and we added a NOT gate, the result is always going to be 1, of course. So this is the most simple Java application using strange that's that's applying gates onto a qubit. So this is the low level usage of the strange APIs. As I said, this is probably not something that every Java developer wants or should know. So the very often in Java, the higher high level APIs shield you from the low level details. For example, the Java enterprise developer who wants to connect to a remote microservice or website or API or so is not creating a low-level socket and applies TLS and handshaking and so on. It just uses the Java URL object, which will then do everything for him. And similarly, typically in Java applications, I don't think gates should be exposed. So, and that would allow software developers to focus on the challenges that they need to address and not think about the low-level gates in quantum computing. Now, I personally think that understanding this and that also in general, if you understand the low-level concept, it will help you in achieving your goal easier, because then you know what tools you can use for what purpose. Especially in those very early days of quantum computing, I think the low-level programming is really how people get familiar with the concepts, and it's fun. But still, in the end, I think what most Java developers want is a high-level API that's under the hood using low-level functions. So the application that I just showed is low-level, but you could have a high-level API that contains then these low-level implementations. And the high-level API, what you saw in the low-level example is that we had a qubit object, and we had gates like the C0 or the poly X gate. And this is something that you would not see in the high-level APIs. There you would see just Java types like int, strings, functions, and so. So I'll switch to my NetBeans IDE to show some more examples. I'll probably need some help from the audience now, because I think you still see the slides, right?
Yes.
Okay, then I'll stop sharing and I'll start sharing again with what you will see from NetBeans. Okay, do you see the my NetBeans IDE, and I will make it bigger?
Yes.
Okay, let me. It's probably best that I increase the font size a bit. Oops. Okay. Oh. Going crazy. Yeah, hopefully it's better now. So what you see here is one of the examples that I have in a repository called QKD, quantum key distribution. It contains a number of standalone files, just Java files, and the first sample is actually what you saw on the slide. So it's just creating a program with a single step, a single gate, and it will execute that gate. I will. I'm not sure that if I run it, that because the result will be in a different UI. So let's see if that's something that you can see. If I run the non-UI version, then you would see the it here below in the output. So let's run this application, and what you see here, I hope it's readable. After applying a poly X gate to a qubit in state 0, its measured state is 1. So this actually shows that that it is working, because we had this qubit that was initially 0, and then we change it. We apply this gate, and the state is then 1. That's of course very very simple. I think I'll just make an edit here to show what we can do. We can create another step, step 2, and oops. It's also a new step, and for this step 2, we can add another gate. If you can see here the difference, we can choose add gate and then a single gate, but we can also add multiple gates simultaneously, which allows for much more concise development. But let's just add another X gate, the X gate which is going to flip the value of the qubit again, and then we have to add that step to the program. Note that, well, and I will do it right now because this is maybe a bit silly. We can, instead of using the add step, we can use the add steps method, and we add step 1 and we add step 2, and then we don't have to add that first step anymore. Apart from that, the rest is simple, stays the same. So we run the program again, we get the qubits, and we measure the value of the first qubit. So if we run this application now, instead, my prediction is that, unless I made a mistake, is that instead of seeing its measured state is 1, it should be its measured state is 0, because we flipped it back from 0 to 1. So let's oops, can I run it here? Okay, yeah. So you see here, its measured state is 0. So that's not really impressive, of course, because this is this is not doing anything fancy with quantum behavior. The NOT gate is the same as it is on classic computing. But if we, instead of adding an X gate, we would add a Hadamard gate, which is the gate that brings a qubit into superposition, then I have no idea what the outcome is going to be now, because this is going to be 50% chance that it will flip the qubit, that it will become in state 0 or in state 1. So I'm going to run this a few times. So you see, we first got it in state 1, we run it again, and it's in state 1. So that's typically when you have to give a demo. And now it's in state 0. So you see that the outcome is now something that would be classically impossible, because we have this gate which brings a qubit in a superposition, which means that if it was 0 or it was 1, it will be in a superposition state. And then when we measure it, it will be either 0 or 1. So that is an example of how you write low-level applications. This is really extremely simple. If you want to see more complex applications, for example, I can show the code, and I can actually also run it for Shor's algorithm, because I have that in the quantum Java in chapter 11, I think. So I'll have to open that. Okay, so this, oops, where is it? Okay. This, all these samples are explained in the book. Let me see. Where do I find? Ah, oh, it has a subproject there. So it's inside of 11, and then it's called quantum factor. Yeah, okay. And actually, this sample is using the high-level strange API. So what we say here is we have in strange, there's a class classic, and that class contains a number of high-level APIs. For example, here is the call to q factor, which will factor an integer. So it will factor 15, and it will do that in. If you run this application, it will show factored it in. Well, 15 in 5/3 or so. But the interesting part here is that I think I have it open already here. Is this q factor method on classic, which is the class that's part of strange. So the q factor method here is, as you know, in Java. Well, pretty verbose, but it also contains explanations. Shor's algorithm for factoring integers contains a classic part and a quantum part. So the classic parts are done well also in Java, and then the quantum part is the part where we need to find the periodicity of the function, and that is done in this find period method, where we also call another method measure period. And what you see here is what we actually did in the simple example as well. So we also created a quantum program with much more qubits. We add Hadamard gates to a number of qubits, and then we add more steps, and we combine gates into blocks. And so this is all low-level strange API. And we, for example, we use the inverse Fourier block as well. And then ultimately, we run the program and we measure all the qubits, and we create an integer value from the result, and we give that back to our application. So this method is the only method in the whole call that is using the quantum computing simulator. So if you, as a high-level Java developer, want to do this factorization, you can just call the classic API, and then you will and that's all that you will have to do, because under the hood, Strange is using the low-level APIs. But if you want to have some fun with gates, it's of course highly recommended to use the approach that we do, for example, here, where you create the low-level program yourself, and where you add gates together, and you do that in a Java approach. So you use your Java skills to create this. The advantage of using the high-level API like here is that this is very easily integrated in an existing backend Java application, because there's no order dependency required. It's just like adding a dependency on another Java framework, and it's actually also good in a way that you do not need access to a quantum computer there, because the low-level implementation, as you can see here, we have a quantum execution environment, which is an interface in Java, and we instantiate an instance of this, and we choose the simple quantum execution environment. But all the operations that we do are on the quantum execution environment interface and not on this particular implementation. So that is why it is possible to also write a cloud quantum execution environment, or and I think I saw a comment about that in the chat, or an or it can be, for example, something that is using QASM, so that the where the simple quantum computing execution environment is simulating the quantum gates, the Java quantum gates into Java arithmetic. It can also be translated into QASM or in any other protocol, or it can run on a quantum cloud service, for example. So just by adding different interfaces, different implementation of this this interface. So the result is that this part of the application, so what you write here, is going to be the same. If you create a different execution environment, then you can target different quantum existing or new quantum computers or simulators. I would like to show finally some of the results if you're using StrangeFX, because that is actually what I think pretty cool, that you can visualize the circuits, because reading this is pretty hard. But if you see, we have here the PolyX sample, but we also have the PolyX UI sample, and that is that's doing more or less the same as the PolyX. Apart from that, in the end, it has renderer.render program, and that will then show the user interface that you saw before, that you saw on the slides. I'm worried that if I'm running this, it's going to show up in a different window. So I'll have to stop sharing and start sharing again to show that different window. But unless I find a way to share the whole desktop, but I wasn't able to find that. But I will do this. I will maybe your screen sharing. No, it's just showing the current screen. Okay, I will do this. I will show one example of how it looks with StrangeFX. I will first show the code of a slightly more interesting sample, and then I will run it and show the user interface. And the sample that I want to show is I have this application in chapter 7. So if you have the book, those samples correspond with the code that's in chapter in the specific chapter. We have an it's called random bit debug. Although it has not much to do with random bits, but what you see here is that we again create a new quantum program with 4 qubits. We add a few steps, and the first step that we add is something with a special gate, a probabilities gate. And this is something that Strange itself will ignore, because it's not changing the state of the system anyhow. It's just something that StrangeFX will use, because it will use that to visualize the probabilities at that particular step. And after that step, we have the real processing, which is a Hadamard gate to qubit 0, a NOT gate at qubit 3, and then a CNOT gate at between qubits 0 and 1. And you see that after each step, we add another probability gate. And this is to visualize how the probabilities change. And then again, we add all the steps to the program, we run the program, and we render the result. But the important part here is that that we add these probability gates. So I will visualize this, and you probably won't be able to see this while I'm doing it, because you only see the code. But once I will run the application, and I think you just have to trust me that I'm running really this application, and then I can share the result, unless it magically pops up on your screen as well, but probably not. So let me stop sharing this and I'll share the result. Oops. Okay, there we go. At least I hope. I guess you're now seeing, yeah, the UI need to be a bit more polished. But what you see here is this 4-qubit system. And if you remember, we added a Hadamard gate on qubit 1 and an X gate at qubit 3, and then a C0 gate between gates 0 and 1. So if you're quantum savvy, you can easily calculate the results by head. But the thing that we added here is that we added these probability gates. So you see here, before we do any quantum operation, the status of the system is in well 0 0 0 0. I'm not going to explain what the probabilities exactly mean. It's all well, there's no magic here again, but this is just to show Java developers that this is sort of the debugging that you would typically use with a Java debugger, where you can follow the values of variables, and with this UI you can follow the probability of values. So the fact that we have two entries that are part, at least for a part filled, means that there are two possible outcomes here, and that is what this visual debugging shows. This is to me, this is really helpful when working with complex circuits that are totally not doing what I would expect, because it's very often to stop halfway in the process and take a measurement, because the moment that you measure something, it's all gone. So you really want to measure the system without really measuring it. And that can be done by, well, showing how likely is it that I'm going to measure this or that there. And that is something that in Java development, IDEs with debugging are extremely important. And so you can do that in StrangeFX as well. And I think that is something that if you want to provide a tool for the Java world, you really need to have this these tools that Java developers are used to, and debugging is one of the very important tools. And I showed you how you can do that in your application. Just add a step with a probability gate, and it will be visualized like this. I think I'll stop with showing samples, but I have much more code that I can show. But I'll go back to this summary where I think yeah. So the potential for quantum computing is huge. Computers are not really there yet. But you can already use simulators and write code for those simulators. I have my coordinates here, and then where the book is available. And I'm very open to questions. I try to follow the chat a bit in the in the meantime, but maybe if there are some questions, it would be good probably to hear them. And I see Ron raised his hand. So
Hi, Johan. It's a pleasure to meet you. I feel I know something about you, having had a few discussions with Professor Barry Bird in our Chicago group about you. Um, I have basically comments about your book real quick and actually a bunch of questions. So I'm going to do the comments in one question and give everybody else a chance. So I read your book cover to cover, which is which is pretty cool for me. So that's how interested I was in it. And I have to say, it's very well written. The text flows naturally. It's very easy to read. Um, I really appreciated your non-hype approach. You make no beans about where quantum is at currently, and your examples are designed to teach, and you're pretty straightforward about that. And even though I'm not really a Java person, I found the code examples easy to read. I do have a background in C and C++, so I didn't have any problems reading your code. So just on those bases, it's really a good book to look at. Um, One of my questions about some of your examples is that there are a number of examples where you use a quantum oracle and you implement it by dropping in a matrix that I guess you sort of manually create the matrix. My question to you is have you done any work or done any research into how one would go about building these oracles from algorithms?
Right, that's a good question. I did some work on having a combination of quantum gates, actually some sort of a subroutine as an oracle. I did not implement that in Strange yet, but I considered it a number of times, and one day I definitely have to do it. And I'm actually, so this is great feedback, because I've been thinking about it as well. The advantage of simply using a matrix as an oracle is that it's simple and it's static. And if it's more an algorithmic or the result of an algorithmic calculation, it's more dynamic. So it's slightly harder, but definitely much more flexible. So yeah, and it's and also from a Java point, it would be it would make for a good interface, because an oracle, which is already an object in Strange, can be constructed then not only from a matrix, but from a function, and that would be very valuable, of course. So I'll put it on a shorter term roadmap. That's actually great feedback.
I appreciate that. I would be actually interested in talking to you further on that subject. I have more questions, but I will let other people talk if they have them.
Actually, I've been discussing with some participants. Do you see any future application developing quantum computing application in Java in the industries, such as in finance?
Yes, yes, that's that is most likely. Java is used very, very very often in financial institutes, and what I hear from big companies doing Java and quantum education, and so is that mainly the financial industry is interested in getting up to speed about the potentials. And it's also, for example, fraud detection, combination of AI and quantum, finding optimization problems, and so that is from from the natural business logical flow, I believe that is currently responsible for most of the interest of the Java industry into quantum computing. And to be honest, I personally I'm more excited about the prospects of quantum computing for healthcare and medical advances and scientific advances and so. But the fact that the same technology is going to be extremely useful for financial information, financial systems and companies is probably good, because that means that there's going to be investment in it, and in the end we can all benefit from that. But indeed, the financial world is finance, and then also logistic and distribution. I know a very large airline company doing lots of research in quantum computing because they want to find the optimal routes and so. But those are indeed the expected first adopters of quantum computing in the how do you call it, the backend is the server industry, where Java has most of its market share, right? So yes, indeed, as I read in the comments there, being backed by finance industry means maybe more dollars into research. That is definitely true. So even if it's maybe less exciting than yeah, all the naive idealistic things that I see, it's definitely true that this can be a major funding source.
So how about Kotlin, Go, Rust languages with quantum computing?
Well, so Kotlin is using the JVM as well, so that's easy. That's covered with the same tools that you do in Java. Rust, I'm not aware of Rust quantum initiatives at the moment. There must be something. I think it would make sense in some of the especially the low-level communication area. I see Rust as very applicable to really low-level device drivers and so. And then it might be good there. But I haven't seen. But I might have missed it. Maybe or if you ask many Python people about Java, they might not know about Strange either. So I'm not aware of major initiatives, but it's definitely something that I would see in the networking part, because what I think the quantum key distribution. Oh, I didn't show it, but it's something that I'm really really excited about, and that needs integration if we want to make that a part of the end-to-end communication stack. Then it needs to be integrated somewhere, well, typically in the kernel or in the networking device drivers. And then that's more the area of C, C++, and Rust. So it would make sense.
Ron, can you unmute and ask question? Can you talk a little bit louder? Your microphone is in a lower volume.
Is this better?
Yes.
Okay.
People can hear it.
Okay, thank you. So my next question has to do with you kind of allude to in the book, and you've kind of talked about it today, is building some sort of transpiler for the Strange framework to something like Chasm. Can you give some information on what the current status of that is? It's something that I've been looking into. I have a background in compiler development, and am currently looking to see if something like a chasm emitter framework would be something that you could plug into that.
Yeah, well, I think Barry put that higher on my agenda recently, but I still had to come to that. But it's I didn't look into chasm itself, although I think it's very very applicable. What I did was I looked at an integration with the tools from Delft University of Technology, where they have distributed quantum computing, because well, they're working on a quantum network that spans European cities over existing fiber. So my idea was that if that happens, then and if we can talk to that network, then that would be an amazing use case already. So that was my the reason why I was more looking into SimulQuant, which was the name of the simulator there. But there's well, chasm is is definitely something that I think it should be doable relatively easy. So maybe we should talk about it offline more. I still had to look into it, but it's definitely one of the quantum execution environments that I'd like to support. And the other was I sometimes would question to ask for interoperability with Qiskit, so that you could run it on the IBM quantum devices natively as well. So it's yeah, to do, but it's good that you ask it, because we have to do it. So let's follow that up, that discussion.
I would be very pleased to talk to you more about that. I think Chasm is kind of a good choice. I understand that it runs directly in the Qiskit environment or the IBM quantum experience, and I'm told by others that it's a language that runs on other quantum hardware directly. You can just take the program over there and run it on trapped ions or other hardware platforms. So that'd be great. I appreciate your input on it.
I see a comment about Penny Lane from Xanadu, and that is something that got my interest as well. The 1-1 mapping would be a bit harder there, but it's definitely also something that I think Xanadu is doing great things. So that's also so these are actually great suggestions, and it means and it's going to be good for Java developers if they can run their samples not just on a simulator but also on on hardware that's sort of available. I just want to make sure that that developers are not disappointed, because what you read in the press might create the expectation that oh, I can create this Shor's algorithm and then I will show off with my friends because I can hack their private keys. That's not happening soon, of course, but it's definitely good to give developers as much opportunities as possible to run the applications. And the abstraction is strange with the quantum execution environment being an interface allows for that. So. And I also see the comment about backed by finance industry is not going to solve the issue that many students are not studying quantum computing. It's definitely true. So I don't want to sound like that funding from financial companies is the only thing that we need. Education is extremely important. I have to. I didn't read the complete comment, so maybe I'm off topic. But I have to say that when I talk about IT, the general audience is different than when I talk about quantum computing. I see much more diversity and students, and so when I talk about quantum computing, so I'm hopeful that that there will be yeah, enthusiasm in education for working with quantum computing and so. And if the question is about about Java at universities and high schools, and so yeah, Java has a major image problem there, and for very good reasons. I think Oracle screwed it big time by only or over focusing on cloud native microservices with Kubernetes for the financial world, and so ignoring the educational market. But it's Java is much bigger than that, and there are plenty of people in education and outside Oracle, but also even inside Oracle now, who are really going or targeting the educational institutions, and so it's extremely important.
But there's a question: does the string simulator calculate solely on the CPU, or is there a GPU mode thinking of bigger and more complex circuits?
Oh, right. Yes. I see the question. I'm sorry, I missed that. At this moment, the simple quantum computing execution environment is only doing the CPU. The rendering is done on the GPU. So StrangeFX is, because it's using JavaFX, is going to use the GPU for doing the rendering and the probabilities and so. But the computations itself are currently only on the CPU. But that's also something that I wanted to change it a long time ago, but then after talking with some evolutions in the OpenJDK, so where Java is developed, Java is getting more native support for leveraging the GPU for calculations, and so it's something that that should be done automatically in new versions of Java. And it will help, but it will help with performance. But the main bottleneck in the simulator is typically the memory, because the more qubits for every qubit that you add, you sort of need to double memory or quadruple, depending if you want to cache intermediate results and so. And that is the main bottleneck. So the speed of computations is typically more or less under control, but 100 qubits are impossible to store in memory. I'd like to and I'm hopeful to leverage more cloud computing. It's something that I'm investigating a bit as well. If we can split the algorithms so that they can be parallelized on two instances, for example, then we can somehow deal with memory problems. But once qubits are entangled, this is of course a completely different question. But I'm reading some papers on about this can be done. But so that's for the memory problem. But indeed, for the computation problem, the GPU is indeed a good suggestion.
I have one last question. It's kind of more technical on the Java side. Again, I'm not a Java person, although its similarity to the C and C++ world helped me get through it. And I'm making an assumption here that Java's feature set enables meta programming techniques like method and object factories. Have you, looking at your examples in your book, I think that they're required to be as straightforward and detailed, which for me kind of makes for a long listing. But I'm wondering if you had looked into using some of the more advanced techniques, if they're available, to use things like method and code factories to streamline the code a little bit.
Yes. Yeah. So that's why I think I showed the example of where you can instead of doing add step, that you can do add steps. But we go even further by actually the whole program with different steps and steps with different gates can be in one line, because there are constructors that what I showed in the samples and also in the book is that you create a step and then you add gates to the step. But if you look at the Java doc, you can create a step and specify which gates need to be added to that step. You can actually create a program, and instead of adding steps to the program, you create a program with the steps that you want. So that pattern is supported as well. And I do realize most Java developers prefer this concise approach, and I prefer that as well, at least once I understand what I'm doing. And that's why I typically start by doing things in different steps and vary for both, and then only later I optimize. And it's the number one critic that I get on pull requests on every project that I'm working on. I almost never return when a method returns something. I almost never return an expression. I always create a variable named answer, and then I return answer because I want to have the debugger in between those lines, or I want to print out something. But I do agree that for for the sake of readability, or not being too verbose, or so, that it's much better to write it more concise. And those patterns are supported. I got help from a good friend of mine who is mainly working with Scala, and so a bunch of patterns that are now in Strange are from his ideas that he had with Scala. So it's definitely the intention to support different programming paradigms.
Yeah, and again, I think it's very necessary for your book that that you have the discrete lines, and it makes it easier for you to comment on everything. And so the one other technique that I forgot to mention was method chaining. I think would be something that you could really streamline the code, and assuming that this would go into production someday, that would be really valuable. So really appreciate the feedback.
Yeah, method chaining is indeed yeah, that would make much chance. Yeah, Fluent API. Yeah. Are there any more questions? If I missed the question, feel free to type it again.
I have a question. Can we download the strange dependency from Maven Central repository?
Yes. So the examples, all the examples have a POM XML, and in the examples you can see the dependency from Maven Central. I think so in the slides, but I will edit the slides before I send them. It has the link to the samples, but I will add the QKD sample, and if you look at any of the samples, the pom.xml file will contain the link to the Maven dependencies. And also, Java developers who like to use JBang can do that. Well, thanks to Barry who showed me the value of using JBang. I have a bunch of samples now with JBang, which means that it's very easy, even for non-Java developers, to execute the samples and to run them without having to install Maven or so. So it's making it as accessible as possible.
So which JDK version is required to run your strange code?
It requires Java 11 or later. So that's yeah. I think Java 11 is has been released many years ago, so it should work for most Java developers. If you're using Java 19, it still works, but Java 11 is the base.
So can we compile your code using GraphVM?
Is the question, can you compile it using GraphVM?
Yes.
Most likely, I did not try this in particular, but we're at Gluon we're using GraphVM extensively, and and we enable GraphVM for JavaFX. So there should not be any showstopper. And it's actually also pretty cool because once you have it compiled in as a native image, then you can easily execute it. So that should be we're not doing reflection, and so it should be should work. And I should do that and document it. Good suggestion.
So it should work using GraphVM to convert from the source code to bytecode to machine native code to the .exe file.
Yes. So what GraphVM is going to do is then compiling the Java bytecode and the native code into a native executable. What GraphVM is not going to do yet, but I talked about it many years ago with some of the engineers there, but then it was so it's definitely not something on their roadmap. But in the end, it would be cool if GraphVM can also compile the logic gate code into QASM, for example. So using the GraphVM compiler to compile it, but that's a major stretch. But it's something that would be cool, but not immediately in the interest of Oracle, I'm afraid, but GraalVM is bigger than Oracle, so it would be a very exciting research project too.
So will Oracle continue to develop Java, like so far with Java JDK 19, but will they have Java 2021 and so on?
Yeah, Oracle, as far as I know, Oracle will continue developing Java. They have $1 billion industry depending on Java. So I think the incentive for keeping developing Java is huge. But the important thing is also that it's not just Oracle. Java is much bigger than Oracle, and JavaVex especially is much bigger. There are so many different companies and individuals that are contributing to Java, and I think that's good, because one company cannot kill Java, and it always scares me if there's a technology that's just supported by a single company. For example, if Google has great technologies, but most of them after a few years land in the Google graveyard. There's a nice website about it where you can find great Google technologies that are then sent to the graveyard. And with Java, Oracle is clearly the biggest investor in it, but there are so many people writing code for it that it's very future proof.
So do you think Oracle will investigate more money on developing quantum computing programming or application using Java?
They did not talk officially about that, so I can't answer that question unfortunately. What I can tell is that there are a number of people in Oracle that are extremely skilled people and very interested in quantum computing and in the Java and quantum computing. But almost everyone in Oracle that I talk to tells me that they cannot speak for Oracle. So I guess it's a question for Larry Ellison or someone else there.
Thank you. So do anyone have any feedback, comments, questions? If not, that's all for today. Thank you for coming.
Thank you very much for having me. Bye.
Bye.